All right, so to get us back into the swing of things here, I figured we would review a couple examples, one from each of the last couple sections. In 4B1, where we talked about a process called substitution, and then 4C1, where we talked about the process called elimination or the addition method. So for 4B1, again, we're going to be using the substitution method for this one. And again, we have covered this before. This is a question directly from your notes. I just figured it's been, 2 weeks. You've had some other things on your minds probably, so thought I'd remind you how this goes in case you'd forgotten any of the details. So for substitution, we want to take one of the equations and solve for one of the variables. And we talked about in class how this right here, the y in the second equation, is really the only good one, the only easy one to solve for. Remember, solve for means get it by itself, get it so it says y equals. So with this equation, we can do that very simply by just subtracting the 2x over to the other side, removes it from there, and we've got y equals negative 2x. Now, the idea was we do this, we solve for a variable because now we know y is the same as negative 2x, and so we can take this negative 2x here, and we can substitute it, hence the name, substitute it into the other equation wherever we see a y, which would be right there. So I can take this negative 2x in place of that y, and if I write this equation, 3x plus 2, but instead of that y, I put in negative 2x equals 1. Then we've substituted into that back into the first equation. And notice the goal here, the reason we did that is because now we have an equation with only one variable in it, just x. So now we can go about solving this equation. 3x, 2 times negative 2 will be a negative 4, so negative 4x or minus 4x. Then simply combine like terms. You can call it negative x or negative 1x if you wanted to. And then to get this solved for x, we can just get rid of that negative sign by multiplying or dividing both sides by a negative 1. End up with x on the left, and 1 divided by negative 1 is a negative 1 on the right. And so we have our first value for x. Now our goal for these is always to get values of x and y, but we can easily do that by taking this number we just found. And we mentioned before that with the process of substitution, this equation that you have solved will always be solved for your other variable, so this number that you got can always go directly in place of that variable in that equation, and you'll basically almost immediately have your other variable, your other unknown. So substituting negative 1 in for that x, negative 2 times negative 1, which would give us a positive 2. And so now we have both our x value and our y value, and we mentioned that with these problems, these systems of equations, we always write our final answer as a coordinate pair, x comma y. So negative 1 comma 2 for our final answer. Also, don't forget, I'm not going to go through these steps, but remember this value of x and this value of y is the pair that solves both of these equations. So you always have the ability to check by taking this x and this y, plugging them in there and there, making sure that's true, and same plugging them in there, making sure that that equation is true as well. It's a very easy way to check your answer in the end. So there's our substitution process. And then this question is example 3 from our notes in 4C1. And again, this process we're going to use here, I call it the elimination method. I believe the author in the book call it the addition method. So with this one, different setup, definitely from the beginning. You're going to look at either your x's or your y's, which should be lined up at this point. X's, y's equal constants. You always want that first. But you're looking at the coefficients of either the x's or the y's, and our goal, remember, was to get those two numbers there or those two numbers there to be the same number but opposite sign. And so we kind of described that almost like thinking about as if you're looking for an LCD, right? The lowest common denominator, even though there's no fractions here. The idea of if you had two fractions with a 2 and a 3 in the denominator, and I asked you what's the LCD, like what's the smallest number they both go into, and the answer would be 6. Here for 3 and 4, the LCD of 3 and 4 would be 12. Now, what we have to remember is we are going to be changing one or both of these equations by multiplying by whatever we need to so that we can make that thing happen. We can make both of these numbers here, the coefficients here or here, have the same number but be opposite sign. Now these are both positive and a 2 and a 3. Here we've got a positive and a negative, but a 3 and a 4. There's not a wrong option. It just depends on what you feel more comfortable with, whether you want to try to aim for dealing with smaller numbers. If that was the case, we would go 2 and the 3, because we just need to make them 6s. If you really want to take advantage of the fact that there's a positive and a negative here, though, we could go with 3 and 4 and work on getting them to both be 12s. In the notes, and for this example, I'm going to go ahead and stay with the x's. I'm going to go ahead and say we're going to take the process of eliminating the x. And to do that, we will need to worry about changing the sign because the 2 and the 3 are both positive. Now, like I said, we will be changing what's on here by simply multiplying. And we said we want these to be a 6, right? A 2 and a 3 have an LCD of 6, meaning I can turn them both into 6s by simply multiplying. So if I did this first equation, I could multiply by a 3, right? 2 times a 3 would make that a 6x. And then down here, this 3x, we would multiply this equation next by a 2 to make it 6x. But again, one of those 6x's has to be negative. We need opposite signs. So I'm going to go ahead and take this equation, the first one, just so I don't forget, I'll say, and I'm going to multiply it by not just a 3, but a negative 3. Okay? So multiplying that equation by a negative 3, every single term, gives me a negative 6x plus 9y equals 3. So there's my negative 6x. And then for the second equation down here, now we just want that to be a positive 6x. So I will multiply by a 2 and get a positive 6x plus 8y equals 48. Again, you're getting these terms of multiplying every single term by that, and then every single term by that. And now that we've done that, we have the setup that we need to do the elimination or the addition step, which is nothing more than adding vertically. These things are all lined up to where a negative 6x and a positive 6x, if you add them, give you 0, right? It goes away. 9 and 8, I will add them and get 17, so 17y. 3 and 48, I will add and get 51, and you will always be left with this very simple equation, basically a one-step and done equation, dividing both sides by that number, 17, to get my y value of 3. Now, just like before, this is one variable. We need to get the other. The only difference is we don't have an equation like we had with the substitution method, where we already have this set up as an x equals. So a little bit of extra work, but not a lot. We'll take this y and plug it back into either one. It does not matter. I'm going to go ahead and just use this bottom equation here. So it'll look like 3x plus 4, but now is where I'm going to plug in that 3 in for that 4 into that equation. So I replace the y with the 3, and now we can continue to solve this. 3x plus 12 equals 24. I can move the 12 over, being left with just 3x equals 12, and then divide both sides by 3 to get x equals 4. And so we have our x value and our y value, which again give us our coordinate point of x comma y of 4 comma 3. And that's our solution.